one thing that pops up from time to time is the Coriolis effect, and you always see these people with basins or toilets or sinks, and they watch the water spin around in them, and they talk about this is because of the Coriolis effect, when in reality, it's not. It's mostly due to the design parameters of the sink or the toilet or whatever. And we can show this with math. So we're going to start by modeling part of a sphere. I draw a sphere. We have three coordinate directions that are relevant. R, we have theta, sorry, this is defined as phi, the textbook that I have, and then we've got theta, which is the angle from the pole. And there are governing equations that we can use to analyze the motion of a liquid as there is momentum, rotation, etc. So first we're going to start with the equations of momentum for a Newtonian fluid with constant rho and mu. We're going to use water. We're going to assume a few properties such as, density is equal to 1,000 kilograms per meter cubed, and the viscosity is 0.001, and that's, I forget the units on it off the top of my head, but I know that that value is right for room temperature water. Right, our spherical coordinates, our equation in spherical coordinates for the r direction for motion is this, and I'll skip to the end of me writing these equations because it's super boring. All right, and there we have all three of the equations. This one is for the r direction, this one is for the theta direction, and this one is for the phi direction. And now we need to ask ourselves what sort of assumptions can we make to simplify this, because I do not want to do an entire CFD. I'm lazy, and it would take up way too much computing power. So let's assume that it's very radially thin. All right, so there will be almost no effects in the r direction. Now I can tell you right away, this is not a good assumption, because in every video you see, there's always a vortex that forms, which is in the r direction towards gravity, towards the center of mass of the Earth. But when people talk about this effect, they're always talking about it in relation to the movement of the Earth. If we make this assumption, we would expect to see that a lot of the motion just doesn't happen because there won't be any radial effects. So if we assume it's a very thin slice, we cross everything that's VR or DDR out, crossing out that pressure term just because if it's very radially thin, there will be hardly any pressure anyway. So I want to point out that even making this assumption, this term up here does not simplify to 0, right? So there will be effects on the radius from the theta and phi directions alone. And this is not surprising if you visualize the rotation of the Earth in your mind and realize that as it rotates, there will be radial effects from that rotation, even if you assume it's a thin layer. Right? And then continuing with this assumption, we can cross out a whole bunch more terms. Gravity does not affect the theta direction. All right, so now that we've crossed out a bunch of terms, let's write the simplified version of our equations. This isn't a calculus tutorial, so I'm just gonna write this out with the chain rule. All right, and now that we've got some useful equations, we can start doing some actual work. The values that we're looking to solve for, more or less, are this value, this value. The reason for this is so that we can use the Euler method, which allows us to determine the next point if we have the derivative at the current point, the time step size, and the value of the current point. So the way that we're going to do this is we're going to set up a grid. It will be a spherical grid. I cannot draw straight lines. I am not. So I'll have a certain number of points on our grid. rows and columns, and I'm not going to spend time drawing these all out. We're going to pretend that these are part of a sphere. This will be along the equator, where that dashed line is, and then these lines will be below it. This way we can get, at this point, theta equals pi over 2, and say phi equals 0, and then it increases this way, and theta increases this way. If we remember back to our geometry, we can determine the values for phi and theta at each point. If we have determined the difference between the distance between each of the points on our grid, then we can overlay that onto a circle, figure out what ratio of that distance to the Earth's total circumference it is, and get the ratio in radians to figure out exactly what angle each point is at. This will allow us to get a phi value and a theta value for every individual point on the grid. And this is important because in the equations that we saw earlier, we saw that we needed to calculate sine of theta and the derivative of various values with respect to theta and phi. So if we calculate the diameter, the circumference of the Earth as 2 pi r, then d over 2 pi r is the ratio. So then we multiply d over 2 pi r times 2 pi radians, and we end up with d over r radians, which gives us the distance in radians between each individual node. This is useful because it allows us to figure out theta for each point, where if we iterate, right, this is or theta and phi, right? So this is phi, and at the next point it's 0 plus d over r, right? And then at the next point it'll be 2d over r. And similarly for theta, this point will be pi over 2 plus r. Then the next one will be pi over 2 plus 2d over r. This is also useful because we need to calculate the velocity of the rotating Earth. We can do this by saying the Earth rotates once around, so 2 pi r every day, 86,400 seconds, if I've done the math right. Radius of the Earth is known to be 6371. So once we do this calculation, we get that the Earth rotates at about 463.32 at the equator, right? So we can use our ratios from the circle above to figure out how fast it is going at each of the different theta levels, right? Because for one theta level, the velocity will always be the same right through here. And then for the next theta level, it'll be a slightly slower velocity. And in theory, if we went on forever, it would just get slower and slower and slower. We could go through the derivation really quickly. The velocity is equal to the old velocity times cosine of d over r, but you increment it for each value. However, because of the way that we've defined theta in this instance, we actually need to do sine of pi over 2 plus d times I over r, where I is that iterative number to give us which row we're on. All right, and then we will code it up in our handy dandy Python. Since Python doesn't have built-in cotangent and cosecant, we just created it ourselves. There's a whole bunch of stuff. If you want to look through this code, I'll probably upload it to GitHub and link it so that other people can look at it. It's really not that interesting. The way that this works is a finite difference method. So what we do is we compare the grid points to each other to determine the derivative with respect to space. Right? We can't really determine it with respect to time, but with space, since we have the geometry of it down, it's a bit easier. So if we know v phi and v theta at each of these points, then we can look back at our equation and look for each of these, d v phi, v theta types of deals. We can go in and compare how each point changes with respect to phi or theta. So let's take this point as an example, and we want to solve dv phi d theta, that point. What we will do is we will look at its neighboring points for this comparison, right? This is the theta direction. We're dealing with d theta, so we're going to look at the other points in the theta direction exclusively. And we want to know how it changes with respect to space. What we're going to do is we're going to say v phi at I plus 1 minus v phi at I minus 1 divided by 2 times d is going to be approximately equal to dv d theta for this point. This is a pretty well-known method of doing things. I honestly don't want to get into the math of it. The reason it's approximate is because there is actually some error. You know, it's plus some other term, and this gets really complicated if you try to go really, really deep into it, but for the most part, truncating it is fine. The method I used here is known as the central difference method. If we're at one of the edge points, you can't do either I minus 1 or I plus 1. And there's a different equation that's used to deal with this, right? This is called central. Forward is vi plus 1 minus vi over d. And then there's backwards difference, which is vi minus vi minus 1 over d. And this is very useful for a lot of things. Unfortunately, it's just an approximation, so we're going to have to bear that in mind. There is some error that is associated with this. Now, if we want to do a second order derivative, right, which we need for the equations I showed earlier, we have a similar thing. I'm not going to go through the derivation of it. I'm only going to show the central difference method, right? This is and there's a similar format for the second order forward and the second order backward. And I did implement those in the code. I just don't really feel like showing them here. Once again, there is some error associated with this. I'm not really going to get into that. We're going to assume that it's close enough. And if it looks bad later, then we'll figure that out and we'll make a note of that. All right, so looking back at our explicit Euler method, this might not be the world's greatest notation for it, but it's gonna have to do because I'm not bothering looking it up. All right, so now that we know this and we can get all these other derivatives, in every single one of these, I'm not gonna underline all of them, but I'll try to highlight as many as I can while I talk. Now that we have these, we know theta at each point. We can use the old velocities at each point also to fill in all the rest of these values. The radius is the same for every point, and I think that's and we know the viscosity and the density because we're assuming that those are constant. That's probably a decent assumption. Liquids don't generally change density unless there's a big temperature gradient, and the viscosity is going to be more or less the same. So now that we have all these, we can solve for every one of them in our code. These lines are the ones where I put in those big nasty equations and I solved for dv theta dt and dv phi dt. Now we can go up here. We can figure out just how big we want this to be. I have in here 20 rows and 20 columns. We have the radius of the Earth in meters. We've got 10,000 as a starting node length. I'll make that smaller in a second. We've got density of water in kilograms per meter cubed. Got the viscosity of water right there, and I still don't remember the units for it. We can set a different time step if we want. We can say 10. And then that's the period, right? How long the Earth takes to rotate once. I mean, it's technically not 86,400, but we're just going to assume. All right, so let's set the node length to 10. So the distance between each node will be 10. So we will have 200 square 200 in each direction, so 1,000 square meters that we can look at, and we'll just run this and see what happens. All right, so we can look at these plots. This is what's known as a vector plot, if I'm remembering correctly. Basically, it's showing at each of the nodes has an arrow. and the arrow points in the direction of the velocity. So this is the initial point, right? The Earth was spinning. We're assuming that it all started out at the Earth's rotational speed. So these arrows, while they look about the same size, they're really not. You can see that below. I will scroll up to find, here you go, the initial set of data. It got cut off, but that's fine. So you can see this is one set, right, where it's not moving in the theta direction, but it is moving in the phi direction. And then as it moves down, each one gets slightly slower than the one above it. This is expected. This is not a surprise. And then the final conditions, we can see that the phi values did change slightly. Right? These are not the same, I don't think. But it's hard to scroll up and down and up and down. 3, 2, 4. All right, so these are not the same values, but if you look, they're approximately the same values. We did get a change in the theta direction, however. This is not 0. It may as well be 0, but it's not 0. This first line at theta equals pi over 2, we're going to ignore that because weird things tend to happen at zeros like that. This data is much more useful, where we see values on the order of 10 to the negative fifth. These are negative, they're pointing down. This is expected, right? From the Coriolis effect, we would expect that if we have the equator, that these faster ones will move out away from the equator, and that the slower ones will go like this. And this is essentially what we see here. I don't think that our scale is large enough to get the little bit that goes back around, right, through here, like the parts that will start to actually form a circle, because this is a rather small scale. I mean, it's big in terms of what we normally deal with, but in terms of the size of the Earth, it's pretty small scale. Currently showing the final value. As you can see, it's approximately the same. It's all the arrows are mostly horizontal anyway, and I will show on an extraordinarily small scale. We'll look at something more like the scale of, our swimming pools. Right, so this gives us 160 square meters, which, is not necessarily the size of a swimming pool. So no. All right, and once again, we see that there's hardly any vertical impact on it. Once again, there is still change. We see that it is in fact different. There is something going on, but it's so small that it may as well be negligible. So big scale, small scale, it doesn't really impact it that much. Now, if we try something big, like on the order of 1,000, right? So this gives us 20,000 in each direction. Now we can start to see a few bigger numbers showing up. No longer are we dealing with 10 to the minus 5, right? This is 10 to the minus 2. Here we will try the same large 1,000 on a larger time scale. We've increased the dt to 120 seconds. And as we can see with these final values, there are a lot more important, well, more impactful values. Right now we're on the scale of 10 to the minus 1, which is significantly more impactful. But keep in mind, we had to increase the size scale and the time scale to get to this point. We can conclude that radial effects are important, right? So when there's a drain, which causes a vortex, that's a special condition that my code was not looking at. It completely ignored the radial direction as per our assumptions earlier. We can assume we can conclude that radial effects are important. And the reason for this is that we see this in our sinks and our tubs. We actually see that the radius, the vortex, once it starts, it doesn't stop spinning in that direction until the sink is empty. So once it starts spinning in one direction, it continues to spin in that direction. The second thing we can conclude is that size is important. The size, the scale, is important. Sorry, Master Yoda, you are wrong. There are a lot of other effects, right? Because these equations, we cut out pretty much everything. Cut out weather, cut out radial effects, we cut out tidal effects. And we can also conclude that on its own, the Coriolis effect is not super strong. Yes, it is there. Yes, it is important. It's more important on longer time scales and larger time scales. It is impactful, but on its own, just rotation from the Earth is not going to create super strong effects. And so all the stuff you see about toilets and, sinks and bathtubs, it's all a bunch of hokum because literally almost anything else is going to impact that flow more than the Coriolis effect. Whether it be you pulling the plug out of the bathtub, whether it be you impacting the flow from the sink, right, as it comes out of the faucet if you touch it. So yes, it has an effect, but it's not nearly as strong as everyone tries to pass it off to be.